Okay, I think yesterday I was discussing about this narrowband, not narrowband, the noise equivalent bandwidth, right? Okay, of course, I have discussed about white noise, right? And the two examples, ideal low pass filter and then RC filter. Then I said what is noise equivalent bandwidth, right? So how do we define the noise equivalent bandwidth? So this is the definition. So B is equal to integral from 0 to infinity h of f square into df divided by square of 0. What is this h of f? H of f is the transfer function, right? H of f is the transfer function of the arbitrary low pass filter. This is what is written here, isn't it? It is the transfer function of the arbitrary low pass filter. Okay, and h of 0 is what? Is a low pass filter zero frequency response. It is h of 0 is a zero frequency response, the bandwidth of B, right? So this is the graph of illustrating the definition of noise equivalent bandwidth. Okay, so similar to this, as I said, we will be able to define what is noise equivalent bandwidth for the band pass filter also. Okay, this is especially for low pass filters. Right, let us try to understand how do we define the noise equivalent bandwidth for the band pass filter. Okay. The receiver of any communication system will have some provision for pre-processing the received signal. Okay, you consider any communication system. Okay, in that the receiver will have the provision for pre-processing the received signal. That the pre-processing makes the form of narrowband filter, okay, whose bandwidth is large enough to pass the modulated component of the received signal, okay, undistorted, but not so large as to admit the excessive noise through the receiver. Means what I mean to say is that pre-processing, okay, steps in the receiver, okay, take the form of what? Narrowband filter, and its bandwidth will be large enough to pass the modulated component of the received signal, okay, undistorted, but not so large as to admit the excessive noise through the receiver. So that is what this one. So this noise process appearing at the output of such a filter is known as the narrowband noise. Okay, so I hope, is this clear, the definition of narrowband noise? What I said, the receiver of any communication system will have the provision for pre-processing of the received signal, right? That pre-processing, okay, take the form of what? Narrowband filter, and its bandwidth will be large enough to pass the modulated signal, right, of the received signal undistorted, but it will not be so large, means its bandwidth will not be so large to admit the excessive noise through that receiver, right? The noise process appearing at the output of such a filter is known as the narrowband noise, we say. Okay, I will show you the diagram, whereas we have taken the spectral component of such a narrowband noise, right, which is concentrated about the midband frequency of plus or minus Fc, right? And we found that the sample function n of t of such a process appears similar to the sine wave of frequency Fc. Okay, so let me show the diagram. So this is the power spectral density of the narrowband noise. Okay. What I wanted to say is this is the power spectral density of the narrowband noise. Okay, this diagram. So which is centered at frequency plus or minus Fc, I said, right? This is plus Fc and this is minus Fc, and its bandwidth will be how much? 2b, because Fc plus b, right, minus of Fc minus b, means minus Fc plus Fc will get cancelled, so we'll get a bandwidth of 2b, right? That is what I said here. I think here somewhere we said na midband frequency of plus or minus Fc having a bandwidth 2b. Okay, right? So this is the power spectral density of the narrowband noise we write, and this one is a what? This is the sample function of that narrowband noise. as I said, it resembles the shape of the sinusoidal function, okay, having a frequency of fc. Okay, this is fine. So the power spectral density narrow band, okay, noise will be appearing at plus or minus fc with a bandwidth of 2b, we can say. Okay, and its sample function of the narrowband noise will be what? Similar to a sinusoidal wave of frequency fc, right, which undulates slowly in both amplitude and as well as phase, we say. Okay, undulates means what? Variation, right? Means its phase and amplitude will be varying, right? So here variation of amplitude is shown and variation of the phase also. Fine. To analyze the effects of this narrowband noise on the performance of the communication system. Okay, so we need a mathematical representation of that. Means how do we represent the narrowband noise mathematically, right? So that depends on the application of interest. Okay, so there are two specific representations of the narrowband noise. One is the narrowband noise is defined in terms of a pair of components known as in phase and quadrature components. Okay, in phase and quadrature phase components. This is one way of representing the narrowband noise. Another way is it is represented in terms of envelope and the phase. Okay, envelope and the phase. Yes, these are the two different representations of the narrowband noise. One is what? The narrowband noise can be represented in terms of what? In phase and quadrature components. Second one is the narrowband noise can be represented in terms of envelope and phase. So let us try to understand how do we represent the narrowband noise in terms of in phase and quadrature components and as well as in terms of envelope and its phase. Okay. So if we consider, so let us first consider the first one, that is the representation of a narrowband noise in terms of in phase and quadrature components. Okay. So if I consider a narrowband noise n of t of bandwidth 2b, right, centered on frequency fc, which I have already shown in the previous diagram. This diagram. Okay. This is a narrowband noise, right, centered at frequency plus or minus fc, having a bandwidth of 2b. Okay, this is fc minus b and this is fc plus b. No? So bandwidth will be 2b. Okay, sorry. Bandwidth will be, I can say it is 2b. 2b is the bandwidth. Okay. Right. So this is what I considering here for this one. So I can represent that narrowband noise in a standard form as, so n of t will be equal to ni of t cosine of 2 pi fct minus nq of t sine of 2 pi fct. Okay, so this is the standard or canonical representation of the narrowband noise in terms of in phase and quadrature phase components. So this ni of t is known as the in phase component of n of t, and this nq of t is known as the quadrature component of n of t. Okay, both this ni of t and nq of t are the low pass signals. Right. So why this is ni of t as in phase component? Because it is associated with cosine function, and nq of t is associated with sine function. Right. Cos and sine having a phase shift of how much? 90 degree. Right. So this is how we represent the narrowband noise in a standard form or canonical form. So n of t will be equal to what? Ni of t cosine of 2 pi fct minus nq of t sine of 2 pi fct. Right. So as I said, ni of t is called the in phase component of the noise, narrowband noise, and nq of t is known as the quadrature component of the narrowband noise. both this Ni of t and Nq of t are the low pass signals. So this is how we represent the narrowband noise in terms of in phase and quadrature phase components. Yes, is this clear? Yes, I'm asking you people, is this clear or do you have any doubts in saying how do we represent the narrowband noise in terms of in phase and quadrature phase components? This is what the formula. Yes, shall I go to the next slide? Hello? Hello?
Yes, sir.
Yes, sir.
Okay. So, shift ಆದ್ಮೇಲೆ ಹೇಳ್ತೀರಾ ಎಸ್ ಸರ್ ಅಂತ ಹೇಳಿ. Okay. Fine. So let us see. This is the diagram which we use for generating and extracting the in phase and quadrature phase components. See the second diagram. Okay. The second diagram. First, let us consider the second diagram. Okay, this is used for generating the narrowband noise. So how do we generate N of t? So just now I said the expression for N of t, right? In the previous slide. So N of t is what? Ni of t cosine of 2 pi f ct minus Nq of t sine of 2 pi f ct, right? So I can generate this signal narrowband noise by what? By taking in phase component Ni of t, multiply that with the cosine function cos of 2 pi f ct, right? Then take Nq of t, multiply that with sine of 2 pi f ct. Then use a summer, right? You do the subtraction of these two products, you'll be getting the N of t. This is the diagram for generating the narrowband noise. Okay. Then if I have a narrowband noise, then how do I extract the in phase and quadrature phase components? For that, this is the diagram. Okay. Means here I am applying N of t as the input, right? Narrowband noise is the input. Then what I do? I multiply this narrowband noise. That is already I said what is the expression, right? So N of t will be equal to Ni of t cosine of 2 pi f ct minus Nq of t sine of 2 pi f ct, right? That will be multiplied by this one, 2 cosine of 2 pi f ct. Then I get a product here, right? That product will be positive through a low pass filter. Then I will be getting the Ni of t. Already this type of this one you have done in DSBC and other things, right? So you do that. Get the expression for N of t. You multiply that N of t equation by 2 cosine of 2 pi f ct. And after getting the product, okay, when you pass it through a low pass filter, means higher frequency component will be eliminated, only the low frequency component will appear at the output of the low pass filter. So that we get Ni of t. If I don't use here multiplication factor as 2, then I will be getting here Ni of t by 2, right? To overcome that problem, I am multiplying it by 2 here, that's all. Similarly, if you multiply this N of t, okay, N of t by this one, what is this? I think, yeah, two things I'm showing here, right? By minus 2 sine of 2 pi f ct, right? Then that product will be positive through a low pass filter. So it will eliminate high frequency components. I get only the low frequency component, which is Nq of t. Right? As I said, Ni of t and Nq of t are the low pass signals. So can you do this? Just I have written what is the expression for Ni of t right here. That N of t, that is Ni of t cosine of 2 pi f ct minus Nq of t sine of 2 pi f ct. You multiply this equation by what? By 2 cos of 2 pi f ct. You just see what you will get here at this point, right? Then when you pass that signal through a low pass filter, you should get only Ni of t. Similarly, you multiply that N of t by this one, minus 2 sine 2 pi f ct. See what is the thing you are getting here, right? Then when you pass that signal through a low pass filter, you should get only Nq of t. So this is not done by me, so you can do that. Okay, just simple multiplication. I think you people should be able to show that multiplication and what are the terms you get. Then how do we say that only we get Ni of t after passing it through a low pass filter? Okay. So I want some people to show by switching on their camera. I will give 2 minutes time to do that calculation. I will call randomly. They should switch on their camera and they should show that calculation. I hope everybody is doing it. When I ask you people, you should not say still I am doing it. Yes. Shall I ask somebody, or you will voluntarily present it? Yes, Ashwini, can you show? Ashwini C. Gujar, can you present, ma?
Sir, I'm doing.
Huh? Still you are doing it.
Yes, sir, I'll show once.
What about Chandrika? Yes, Chandrika. Ananta Butputa meeting. Yes, Chandrika Murthy. Chandrika is not there. Yes, what about Sujan? Sujan.
Yes, sir. Martin, sir.
ಮಾಡ್ತಾ ಇದೆಯಾ ಮಲ್ಟಿಪ್ಲೈ ಮಾಡ್ತಾ ಇದೆಯೇನಪ್ಪ ಅದನ್ನ ಎನ್ ಆಫ್ ಟಿ ನ ಕಾಸ್ ಇಂದ ಮತ್ತೆ ಸೈನ್ ಇಂದ ಎಸ್ ಹೌ ಮಚ್ ಟೈಮ್ ಇಟ್ ಟೇಕ್ಸ್ ಇಟ್ ಎ ಮ್ಯಾಟರ್ ಆಫ್ 2 minutes ದಟ್ಸ್ ಆಲ್ see if I multiply this by 2 cosine of 2 pi of ct, what you will get? First term 2 into ni of t cos square 2 pi of ct minus nq of t sin 2 pi of ct into cos 2 pi of ct, right? 2 into nq of t sin 2 pi of ct into cos 2 pi of ct. So here in the first term you will get what? 2 ni of t into cos square 2 pi of ct now. So cos square 2 pi of ct means cos square theta can be written as 1 plus cos 2 theta by 2. Okay, so if I substitute that, what I can write, the 2 will get cancelled, we will be getting only ni of t into then ni of t cos 4 pi of ct we can write, right? Then minus here 2 into nq of t sin 2 pi of ct into cos 2 pi of ct means it is what? Sin a cos b or cos a sin b. Is that what we can write? Yes, 2 sin theta cos theta. You cannot take because a and b are same, so it is in terms of what? 2 sin theta cos theta. 2 sin theta cos theta can be written as what? 2 sin a cos a. Yes, so many times it has come like this. Or sin a cos a will be equal to what? Yes, quickly people should say 2 sin A cos A. Ananta. Yes, Ananta.
Yes, sir.
ಮಾಡಿದೇನಾ ಮಲ್ಟಿಪ್ಲೈ ಮಾಡಿದೇನಾ? I said you multiply n of t by 2 cosine of 2 pi f ct and just check what are the terms you get. Then when we pass it through a low pass filter, I should get only ni of t. Already I said after multiplication what you will get anta. When I multiply that n of t by 2 cosine of 2 pi f ct, I said the first term will be 2 ni of t cos square 2 pi f ct, then minus 2 nq of t sin 2 pi f ct into cos 2 pi f ct. Right? So when we come to the first term, cos square 2 pi f ct means that is cos square theta. If I take 2 pi f ct as theta, then cos square theta. Right? Cos square theta can be written as what? 1 plus cos 2 theta by 2. So if I substitute that, then I will be getting what? 2 into ni of t by 2 plus 2 into ni of t cosine of 4 pi f ct by 2. Okay, then minus 2 nq of t, then 2, that is sin A cos A. Sin A cos A can be written as what? 2 sin theta cos theta. Is it sin 2 theta? Yes, respond. No? Can you write the 2 sin theta cos theta can be written as sin 2 theta?
Yes, sir.
So with respect to that, what we can write? 2 means okay, nq of t sin of 4 pi f ct, right? So when I pass that signal through a low pass filter, I will be getting only ni of t. Okay, is that clear? The first term. Similar to that, if you multiply n of t by minus 2 sin of 2 pi f ct, okay, we get the terms, right? And when I pass that through a low pass filter, I will be getting only nq of t. ಇಲ್ಲಿ ತೋರಿಸ್ತಾ ಇಲ್ಲ ಯಾರು ಏನು ಮಾಡಿದ್ದು ಅಂದ್ರೆ ಮಾಡ್ತಾ ಇಲ್ಲ ಅಂತ ಅರ್ಥ. ನೀವು ಯಾರು ವರ್ಕೌಟ್ ಮಾಡ್ತಾ ಇಲ್ಲ. ಸಿಂಪಲ್ ಮಲ್ಟಿಪ್ಲಿಕೇಶನ್ ಅಂಡ್ ಅಪ್ಲೈಯಿಂಗ್ ಬೇಸಿಕ್ ರೂಲ್ಸ್. ಎಸ್ ಚಂದನ, ಕ್ಯಾನ್ ಯು ಪ್ರೆಸೆಂಟ್? ಚಂದನ.
Yes, sir.
ಮಾಡಿದ್ದೀರಾ ಮಲ್ಟಿಪ್ಲಿಕೇಶನ್ ಮಾಡಿದ್ದೀರಾ?
No, sir.
ಮಾಡ್ಲಿಲ್ವಾ ಮಲ್ಟಿಪ್ಲಿಕೇಶನ್?
ಇಲ್ಲ ಸರ್ ಮಾಡಿದ್ದೀನಿ.
ಪ್ರೆಸೆಂಟ್ ಮಾಡ್ತೀರಾ? Is it possible to present from your side by switching on camera?
No, sir. I didn't solve it, sir.
ಸಾಲ್ವ್ ಮತ್ತೆ ಏನ್ ಮಾಡ್ತಿದ್ದೀರಾ? ಸುಮ್ಮನೆ ಕುಂತ್ಕೊಂಡಿದ್ದೀರಾ? See, those are basic simple things, no, done so many times. That is why I am not doing it again and again. So I am asking you people to do simple multiplication and substituting basic rules and simplifying it. Only if you do it, then the picture will be clear, right? So ನೀವು ಮಾಡಿಲ್ಲ ಹಂಗಂದ್ರೆ, ಚಂದನ ಅಂತ ಸ್ಟೂಡೆಂಟೇ ಮಾಡ್ತಾ ಇಲ್ಲ ಅಂದ್ರೆ ಬೇರೆ ಸ್ಟೂಡೆಂಟ್ಸ್ ಇನ್ಯಾರು ಮಾಡ್ತಾರೆ? What about Manusri? Have you done it, ma? Manusri. Yes, Manusri.
Sir, doing it.
ಇನ್ನೂ ಮಾಡ್ತಾ ಇದೀರಿ? ಎಷ್ಟಾದ್ ಮಾಡ್ತೀರಿ? ಅದು 10 ನಿಮಿಷ ಆಗುತ್ತೆ ಅನ್ಸುತ್ತೆ. Multiplying n of t by 2 cosine of 2 t. ಮಾಡ್ಬೇಕಲ್ವಾ ಬೇಗ ಬೇಗ. What about others? ಸ್ಕಂದ ಮಾಡಿದ್ಯಾನ?
ಸರ್ ಸರ್ ಮಾಡ್ತಾ ಇದ್ದೀನಿ.
ಇನ್ನೂ ಮಾಡ್ತಾ ಇದೀಯ? ಇದೆ 10 ನಿಮಿಷ ಆದ್ರೂ ಮಾಡಲ್ಲ ಅನ್ಸುತ್ತೆ.
ಸರ್ ಇಲ್ಲ ಸರ್, ಇವಾಗ ಸ್ಟಾರ್ಟ್ ಮಾಡಿದೆ. ಅದಕ್ಕೆ
ಇಷ್ಟೊತ್ತು ಹೇಳ್ಬಿಡಿದೆ ನಿಮಗೆ.
ಸರ್ ಅದು ನೋಡ್ತಾ ಇದ್ದೆ ಸರ್.
ಏನ್ ನೋಡ್ತಾ ಇದ್ದ?
ಹಳೇದ್ ನೋಡ್ಕೊಂತ ಇದ್ದೆ ಸರ್, ಹೆಂಗ್ ಮಾಡೋದು ಅಂತ.
ನಾನು ಹೇಳ್ತಾ ಇದ್ದೀನಿ, ನಾನೇ ಮಲ್ಟಿಪ್ಲಿ 2 ಸರ್ತಿ ರಿಪೀಟ್ ಮಾಡೋದಾಯ್ತು. ಅಂದ್ರೆ ಕೇಳಿಸ್ಕೊಂಡಿಲ್ಲ ನಾನು ಹೇಳೋದು. ಎಸ್, ವಾಟ್ ಅಬೌಟ್ ಕಾರುಣ್ಯ?
Yes, sir.
Have you done, ma?
1 second, sir. I'll tell. I'm
1
almost.
second. Okay. Okay. Leah. Yes, Leah.
Yes, sir. One
Have you
minute.
done? Only 1 minute. Karanya 1 second. ಇನ್ನು ಬೇರೆಯವ್ರು ಮಾತಾಡಿಸಿ ಇನ್ನು ಎಷ್ಟು ನಿಮಿಷ ಕೇಳ್ತಾರ ಗೊತ್ತಿಲ್ಲ. ಮಾನಸ ಆರ್ಯ, ಮಾನಸ SH, ಮಾನಸ SH ಮಾಡಿದೀರಾ?
Yes, sir.
Can you present?
Sir, no camera.
No camera. Okay, so easy. What about Manas Arya?
Sir, doing it, sir.
ಮಾಡ್ತಾ ಇರಿ ಆರಾಮಾಗಿ ಟಿವಿ ನೋಡ್ಕೊಂತ. ಟಿವಿ ಹಚ್ಚಿದ್ರೆ ಅನ್ಸುತ್ತೆ ಮನೆಯಲ್ಲೇ ಅಲ್ವಾ? ಓಕೆ, ಯಾರ್ದು ರೆಸ್ಪಾನ್ಸ್ ಮಾಡಿದವ್ರದ್ದು ಕ್ಯಾಮ್ರಾ ಇಲ್ಲ, ಮಾಡದೇ ಇರೋರು ಇನ್ನು ಮಾಡ್ತಾ ಇದೀನಿ ಅಂತಿದ್ದಾರೆ. ವಾಟ್ ಎವರ್ ಉಶಾಂಕ್. ಎಸ್ ಉಶಾಂಕ್. No response. Subiksha.
Yes, sir. 1 second.
You 1 second. Yes, Karunya 1 second is over now. You can present, right? Not 1 second, 1 minute over. Karunya.
Yes, sir. Yes, sir. 1 minute, sir. I made a mistake.
Yes, what about Vishal? Vishal.
Sir? Sir, I
What?
got disconnected 5 minutes ago. I'll do it, sir. 2 minutes.
ಬಿಡಪ್ಪ, ಆಯ್ತು. ಹಂಗಂದ್ರೆ ಇಷ್ಟೆಲ್ಲ ಮಾಡ್ಬಿಡುತ್ತೆ ಅಷ್ಟೇ. ಸೆಮಿಸ್ಟರ್ ನೆಕ್ಸ್ಟ್ ಜೂನಿಗೆ ಎಂಡ್ ಆಗೋಕ್ಕಾಗತ್ತೆ ಹಿಂಗೆ ಮಾಡ್ತಾ ಹೋದ್ರೆ ಅಲ್ವಾ?
Sir, I was there, sir. Just 3 minutes ago, I got disconnected.
Yes, what about Prajwal?
Yes, sir, doing it, sir.
ಇನ್ನೂ ಮಾಡ್ತಾ ಇದೀಯನ? ಎಷ್ಟೊತ್ತು ಬೇಕಾ ಮಾಡ್ಲಿಕ್ಕೆ? ಪೃಥ್ವಿ.
Sir, I'm not done it, but I can tell orally, sir.
ಬೇಡ ಅನಿಸ್ತದೆ. ಸಿಂಪಲ್ ಅಲ್ವಾ? ಯಾಕೆ ಮಾಡ್ಬೇಕಂತ? ಏನ್ ಕಾಸಿಂದ ಮಲ್ಟಿಪ್ಲೈ ಮಾಡಿದ್ರೆ ಕಾಸ್ ಸ್ಕ್ವೇರ್ ಬರುತ್ತೆ. ನೆಕ್ಸ್ಟ್ 2 ಸೈನ್ಗೆ ಕಾಸೆ ಮಾಡ್ಬೇಕು ಒಂದ್ಸರ್ತಿ.
Sir, actually, I can't write. No, sir.
ಅದಕ್ಕೆ ನಿಮ್ ರೈಟಿಂಗ್ ಅಷ್ಟು ಚೆನ್ನಾಗಿಲ್ಲ. ಸೋಮಾರಿ ಅನ್ಸುತ್ತೆ ಬರೆಯೋದ್ರಲ್ಲಿ ಅಲ್ವಾ? ಸೊ ಬರೆದು ಪ್ರಾಕ್ಟೀಸ್ ಮಾಡಿದ್ರೆ ರೈಟಿಂಗ್ ಆಲ್ಸೋ ವಿಲ್ ಇಂಪ್ರೂವ್. ಹ್ಯಾಂಡ್ ರೈಟಿಂಗ್.
Sir, I'll show, sir.
Yeah, please present. 1 minute, I will pin. Yeah. Without shaking, you should. Then only I will be able to see. Otherwise, it will be blur only.
It's fine, sir.
Still, it is blur only. Okay, handshake should not be there. Okay. Okay, you got. I am able to see Ni of T. Okay, fine. Thank you. Okay, then I will continue. Others should do it by yourself. Okay. Okay. So the second circuit. Okay. This one we call it as the synthesizer. Okay, because right means the generation circuit of narrowband noise is known as the synthesizer, and extraction of the in-phase and quadrature components from the narrowband noise component is known as the analyzer. Okay, that is why it is written on the top, narrowband noise analyzer and synthesizer. Okay, so these are some important properties of the in-phase and quadrature components of the narrowband noise. So first one is the in-phase component Ni of t and the quadrature component Nq of t of the narrowband noise will have a zero mean. This is important. Okay, the in-phase and quadrature component of the narrowband noise will have zero mean. Second property is, if the narrowband noise is Gaussian, okay, then its in-phase component and quadrature components will also be Gaussian. Okay, jointly Gaussian we say. Then the third property is, if the narrowband noise is stationary. Okay, I hope you know the meaning of stationary, right? Then its in-phase component and quadrature components are also jointly stationary. Okay, so these three properties I told you. One is it has zero mean, means in-phase component and quadrature component of the narrowband noise will have a zero mean. Second one is what? If the narrowband noise is Gaussian, then its in-phase component and quadrature components are also Gaussian. Third one is, if the narrowband noise is stationary, then its in-phase component and quadrature components are also stationary. The fourth one is, the in-phase component Ni of t and the quadrature component Nq of t will have the same power spectral density. Okay, the power spectral density of in-phase component and the quadrature component will be same. Okay, so which is related by this formula. What is that? Sni of f will be equal to Snq of f, which is equal to Sn of f minus fc plus Sn of f plus fc over this frequency band. Means one will be at plus fc, another will be at minus fc. Okay, fine. Then the next property is, the in-phase component Ni of t and the quadrature component Nq of t will have the same variance. Okay, will have the same variance as the narrowband noise. Then the cross spectral density of the in-phase and quadrature phase components of the narrowband noise are purely imaginary, we say. So that is why we write Sni Nq of f will be equal to minus Snq Ni of f. The next one is, if the narrowband noise N of t, okay, if the narrowband noise N of t is Gaussian and its power spectral density, okay, power spectral density is symmetric about the midband frequency Fc, okay, then the in-phase component Ni of t, fine, and the quadrature phase component Nq of t are statistically independent. Okay, these are some properties of the narrowband noise. One is what? The in-phase component and quadrature component of N of t will have a zero mean. Second one is, if Ni of t and Nq of t of a narrowband noise are Gaussian, right? Right, if N of t is Gaussian, then its in-phase and quadrature phase components are also Gaussian. Right, if narrowband noise is stationary, then its in-phase and quadrature components are also stationary. Third property. Then fourth property is what? The in-phase component and quadrature component will have the same power spectral density, right? And fifth one is, the in-phase component and the quadrature component will have the same variance, okay, as that of the narrowband noise N of t. Then I said the cross spectral density of the in-phase and quadrature components of the narrowband noise will be pure imaginary. Then if the narrowband noise is Gaussian and its power spectral density will be symmetric about the midband frequency Fc, right, then the in-phase component and the quadrature component are statistically independent. Yeah, so these are the key things which you need to understand and remember. This one. Okay, so just we'll have an example about this calculation of narrowband noise. Okay, so let us consider the ideal band pass filter, white noise. Okay, in the previous case we have considered the low pass filter, right? Here we are considering the band pass filter, right? So if I consider the white Gaussian noise having zero mean and power spectral density of N0 by 2, right, which will be possible through an ideal band pass filter of pass band magnitude response equal to 1 and midband frequency Fc with bandwidth 2B. So these are specifications of the filter, right? And I'm telling what is that white Gaussian noise will have. It is having a zero mean and a power spectral density of N0 by 2. That will be possible through the ideal band pass filter. Okay, and the magnitude response of that band pass filter will be equal to 1 with a midband frequency of Fc and bandwidth is equal to 2B, right? So already I have shown what will be the characteristics of that narrowband noise, right? So now our problem is to determine the autocorrelation function, okay, autocorrelation function of that narrowband noise, and as well as its in phase and quadrature components. So this will be a problem. Okay, so they will ask in the exam to determine the autocorrelation function of the narrowband noise and as well as its in phase and quadrature components. Means they will give you the specifications of the filter and they will say what is the input to that filter. So okay, the input to the narrow band pass filter, right, or just we say band pass filter is what? White Gaussian noise, and it has a zero mean and a power spectral density of N0 by 2, right? And here the specification of the filter, right, it is having a midband frequency Fc and bandwidth of 2B and its magnitude response will be equal to 1, we say. So for that we need to find out the autocorrelation function of the narrowband noise and as well as the in phase and quadrature components of the narrowband noise. So once we know what is the power spectral density of the output of the band pass filter, that is right, then if I take the inverse Fourier transform on that, I will be able to get the autocorrelation function. Okay, I think that is what is done here. See, this is the characteristics of the ideal band pass filter, okay, of the white noise. So midband frequency is Fc, this diagram, right? Midband frequency is Fc, bandwidth is 2B, right? And so this is the power spectral density of the what? White noise, which appears okay. So if I know what is the power spectral density of the white noise, which is appearing at the output of the band pass filter, I can determine its autocorrelation function by taking the inverse Fourier transform of this, right? So that is what done is here. See, the autocorrelation function, right? Autocorrelation function of the narrowband noise is the what? Inverse Fourier transform of the power spectral density of the noise. So Rn of tau is equal to, so integral from, so the minus Fc minus B to minus Fc plus B means this frequency is minus Fc minus B, right? This frequency is minus Fc minus B and this frequency is minus Fc plus B. So integral limits and the value of that Sn of f will be what? N0 by 2 into e power j 2 pi f tau into df. That is for this one, right? Similarly, here this frequency is what? This is and this will be Fc plus B and this will be Fc minus B, right? This will be Fc minus B and this will be Fc plus B. So that is what the limits. Limits is written here. See, Fc minus B to Fc plus B and value is N0 by 2 e power j 2 pi f tau into df. So I think in the last class, I think yesterday only I told about this. How do we integrate and say and bring it to the standard sinc function form, right? So if I take this N0 by 2 outside, then you do the integration, right? And you can do that minimum mathematical manipulation and we can bring it to this sinc function form. Okay. So here we'll get one sinc function, here we'll get this one. So here this will be there, e power j 2 pi fc tau and e power minus j 2 pi fc tau. So I get this N0 B sinc of 2b tau. Yesterday we have discussed this, right? How do we get this one? N0 B sinc of 2b tau, right? So in addition to that, here we have what? E power minus j 2 pi fc tau plus e power j 2 pi fc tau, right? If I multiply and divide this by 2, then what I can write? This will be what? E power minus j theta plus e power j theta by 2. This is nothing but cos theta. So that is what is written here. Okay. So since I am multiplying and dividing it by 2, no? So that is why I get 2 here. So 2 n naught b sinc of 2 b tau. This thing can be written as cos theta. That is cosine of 2 pi fc tau. I hope we will be able to do this simple integration. So one step is skipped here. That's all. Just integration, putting the limits and bringing it to the standard this thing function form. That is, you'll get in form of what? Sin pi x by pi x. I hope we will be able to do that. Yes. Integrate this, substitute these limits, okay, and bring it to sin pi x by pi x form. So while doing that, you will be getting this term e power minus j 2 pi fc tau in this, and here you will be getting e power j 2 pi fc tau. So this can be represented as what? Cos theta, right? To represent that as cos theta, what I need to do? I need to multiply and divide by 2. That is why this 2 has come here picture. And this is the autoclash, means it has what? Sinc function, right, along with the cosine. So which is drawn here. Oh, sorry. Okay. So if we consider, see the maximum value is 2 n naught b, right? There is a maximum value. So this is the cosine function, right? I hope we will be able to see this cosine function. I think I will rub this. Yeah. Is able to find out this. See, this is a cosine function. Whatever, just see my cursor, right? This is a cosine thing, right? And this will be a sinc function. Okay, inside that we have written the sinc function. Okay, so 0 crossings. So this bandwidth will be 1 by b from here to here. And this will be the what? This is the in phase and quadrature component of the white noise. That is SNI of f and SNQ of f. So both in phase and quadrature components will be same. That is why it is written from minus b to b as a naught. Okay. Yes, is this point is clear? I hope you have done one more step here. After writing this, you do the integration, substitute the limits. I think 2 steps only. Then 2 to 3 steps, that's all. Then you will be able to bring it to this form. Okay. So as I said, the spectral density characteristics, right, is symmetric about plus or minus Fc. That is the this is the power spectral density of the ideal bandpass filtered white noise. Okay. Fine. So this is the in phase and quadrature phase component I said, and this is the autocorrelation function. This is the autocorrelation function. This is the in phase and quadrature phase component, and this is the power spectral density of that filtered white noise at the output of the bandpass filter. And what we can write is the autocorrelation function of the in phase component and as well as the quadrature phase component will be equal to what? This one, 2 n naught b sinc of 2 b tau. Yes, is this clear? Shall I go to the next slide? I don't know how many of you are able to do this in between steps. Yes, is it done? Shall I go to the next slide? I'm asking. Hello. ಏನು ಶ್ರೇಯಸ್ ಯಾವ ಸೇರಿಕೊಂಡ ಇರ್ಲಿಲ್ವಲ್ಲ ಇಷ್ಟೊತ್ತು?
ಸರ್ ಲಾಗೌಟ್ ಆಗಿತ್ತು, ಜಾಯಿನ್ ಆಗಿದ್ದೆ ಒಂದು 5 minutes ಲಾಗೌಟ್ ಆಯ್ತು.
5 minutes ಲಾಗ. ಸೊ ಮಾಸ್ಟರ್ ಏನು ಅಬ್ಸರ್ವ್ ಮಾಡ್ತಾರಾ ಇಲ್ಲ ಅಂತ?
ಸರ್ ಐ ಗಾಟ್ ದಿಸ್ ಸರ್.
Got that. Okay. Yes, shall I go to the next slide? I don't think you people will be doing the in-between steps because so simple multiplication I asked people have taken so much of time. Shall I go to the next slide?
Yes, sir.
So Shreyas ಮಾತಾಡ್ತಿದ್ದಾನೆ. Okay, take time and do it in your free time. Okay. As I said, only 2 steps are involved here. Fine. That is all about the representation of narrowband noise in terms of in-phase and quadrature phase components. Right. The next one is how do we represent the narrowband noise in terms of envelope and phase. Okay. I said there are 2 ways, right? So let us now try to represent this noise in terms of envelope and phase. Okay. So we can use this expression. We can represent the noise n of t will be equal to like this. What is this? N of t is equal to r of t into cosine of 2 pi fct plus psi of t. Okay. N of t will be equal to what? R of t into cosine of 2 pi fct plus psi of t. So what is this r of t? This r of t is the so this r of t can be written as square root of n square I of t plus n square q of t. Okay. This is the envelope, what we say. This is the envelope. Okay. So r of t is equal to what? Square root of n square I of t plus n square q of t. Then, and this one, this psi of t, no, there is the phase. Okay. So phase will be equal to, psi of t will be equal to tan inverse of nq of t by ni of t. Okay. This is the phase and this is the envelope. Okay, so this is how we represent the narrowband noise in terms of its envelope and phase. So these formulas we should remember. Okay, so n of t will be equal to what? R of t cosine of 2 pi fct plus I of t. I said R of t will be equal to what? Square root of n square I of t plus n square q of t. What is ni of t and nq of t? They are the in phase and quadrature phase components. And psi of t is the phase, right? Which is equal to tan inverse of nq of t by ni of t. Okay. So with this, what I can say is whatever the necessary background which you need for understanding further topics in the module 3, I have thought. Okay. Though you may feel that it is not there in syllabus, but it is required. So without knowing how do we represent noise in terms of its in phase and quadrature phase components or in terms of its envelope and phase, you will not be able to understand the first or subsequent topics in the this module. Okay. So let me now switch over to the receiver model. That is your next topic. Okay. Just I will close this. So let me share another one. Yeah. Yes. So I have written here noise in continuous wave modulation systems, right? So continuous wave modulation means both AM and as well as FM. Okay, we are going to study what is the effect of noise on these modulation techniques. That is on AM, DSBSC, SSBSC, okay, and as well as FM. So for that, first what we need to understand is we need to understand about the receiver model. Okay, so that is what is written here. See, to undertake an analysis of the noise in the continuous wave modulation systems, first and foremost thing is we should have a receiver model. So we should know what is the receiver model, right? And another thing is we are going to okay. So we are going to model the receiver noise or channel noise as the additive, white and Gaussian. Okay, we assume that the channel noise or the receiver noise is the additive, white and Gaussian. Okay, so by assuming this noise as the additive, white and Gaussian, that will simplify the mathematical calculations. Okay, so these assumptions enable us to obtain the basic understanding of the way in which the noise will affect the performance of the receiver. Okay, by assuming the noise is additive, white and Gaussian. Okay, and it also provides the framework for comparison of the noise performances of different continuous wave modulation and demodulation schemes. As already said, we will be discussing about the how does the noise affects the performance of AM, DSBSC, SSBSC and FM systems. Okay, fine. So the idea of the modeling, okay, that is the receiver model we say, right? The idea of the modeling is a fundamental to the study of all the physical systems, including our communication system. Okay. Through this modeling, we will be able to improve our understanding of the capabilities and limitations of the system. Okay, why modeling of the receiver is required is we will be able to improve our understanding of and as well as the capabilities and limitations of that system. Okay. So let us see what is that receiver model is. Okay. So we need to keep these things in mind, okay, while doing the modeling of the receiver. First one is the model provides the adequate description. The model provides the adequate description of the form of receiver noise. Okay, means it will say what is that noise is, whether additive, white, Gaussian, like that. Okay, then the model accounts for the inherent filtering and modulation characteristics. Okay. The third thing is the model will be simple enough for the statistical analysis of the system to be possible. Okay, so these are the three things which we need to keep in mind while doing this receiver model. Okay, so what this is the receiver model. Okay, what I have shown here. So the input to that receiver model is the what? Modulated signal, S of t. Okay, this S of t may be AM signal, or it may be DSBC signal, or it may be SSBC signal, or VSBC signal, or it may be FM signal. Okay, so this is the general receiver model. So we give input to the receiver as what? The modulated signal. Okay, and we assume that the noise will be added. Okay, so that we as the white noise, right? W of t we are writing it. That is why we written summation here. So for this modulated signal, we are going to add the noise, okay, to understand its effect or how does it affects the performance of this receiver. Okay, then output of that will be given to the band pass filter. Okay, so here the band pass filter does the filtering and as well as the amplification of the signal. Okay, then this X of t, okay, is the filtered signal, right? So this X of t will be what? S of t plus W of t, right? Yes or no? X of t will be equal to what? S of t plus W of t. That will be given as input to the demodulator. Even the type of demodulator depends again on the type of modulation. What modulation we use, right? It may be a coherent demodulator, or it may be non-coherent demodulator also. Okay, so just let me brief in means whatever I said here, that I have written in the next slide. Okay, I said so I hope this block is there in your mind. So receiver model means noisy receiver model means the input to that model is the what? Modulated signal. Okay, another input to that is white noise. So we are adding those two. That summation output will be given as input to the band pass filter, right? the output of that band pass filter will be given as input to the demodulator. Then we get the original demodulated signal as the output of the receiver. Okay, as I said, this modulated signal may be AM or DSBSC or SSBSC or VSBSC or FM. Okay, so that is what is written here. See, S of T is the incoming modulated signal, and I said W of T is the front end receiver noise, right? And the received signal will be what? Sum of those two, S of T and W of T, right? I said the band pass filter will be representing what? The combined effect of filtering action of the tuned amplifiers used in the receiver, okay, for the purpose of signal amplification prior to demodulation, right? So the bandwidth of the band pass filter is wide enough to pass the modulated signal without any distortion, right? As I said, the demodulator depends on the type of modulation what we use. Okay, if I use the AM modulation, then demodulator will be of what type? It will be of envelope detector type, right? If I use the DSBSC, then the demodulator will be of coherent type, like that. Okay, and as I said, we assume that noise is the additive, white, and Gaussian, right? Already we are aware what is the power spectral density of this white noise, right? Which is N0 by 2, and what is that N0? N0 is the average noise power per unit bandwidth, right? Which is measured at the front end of the receiver. Okay, I think time is up. I will stop with this. Okay, I will continue with this next. Is it fine?